Hi, dear student, for the General Secondary Certificate Senior 3. Now we will continue our journey together with your syllabus of physics, chapter 2, with the title of The Magnetic Effect of the Electric Current. Dear student, take care of this year due to this year is very important, which will form your future. So I want to remind you that solving problems and understanding exactly the relation between the physical quantities is very important for you to answer the question of physics. Here we will start another journey which has a title Magnetic Effect of the Electric Current. You studied during the lesson 1 the passing of the electric current through a conductor, and this passing through the conductor, of course, due to specific causes and leads to a certain results. And we studied all of these points and we analyzed these ideas clearly during chapter 1. And of course, I'm sure you try to train on solving the problem and the ideas of chapter 1. Now let us start quickly the magnetic effect of the electric current. From the most important point here, the effort of a scientist. Dear student, here the famous one here, its name is Hans Ørsted. This scientist studied the effect of passing the electric current through a conductor. This scientist brought a wire from a copper, as you see in front of you here. This copper wire, of course, a good conductor of electricity. So by passing this electric current, what will happen to the area around this wire? Of course, dear student, you know that passing the electric current change the area around it by producing a certain invisible power. This power is covered by Hans Ørsted by bringing a compass, and this compass, of course, you know, it's a magnetic needle. This magnetic needle is put beside this wire. Imagine here, this is the wire, and there is an electric current I. This current I passes through this wire. Then here, if you brought here something like a compass here, as I'm making in front of you here, this compass has a needle here, the magnetic needle in front of you. This needle will be deflected during the passing of the electric current through the wire. Of course, this needle deflects between two poles, North Pole and the South Pole of the Earth, under the effect of the invisible power, the invisible force which is existed here. This invisible power produced during the passing of the electric current. But the scientist Hans Ørsted wanted to be more sure that the deflection here of the magnetic needle was due to the power from passing the current through the wire here. So he decided to cut the electric current from this wire. After cutting the current from this wire, this needle returned to its original location and its deviation disappeared. This means the force which is generated here was due to the passing of the current through this wire. He called this force by a magnetic force. So he brought a small compass near a wire carrying an electric current and parallel to it. He noticed that the compass needle deflected. He turned the current off. The compass returned back to its original position. So he concluded that the electric current has the magnetic effect. After that, we can't stop at this point only, but we need to find what's the difference between the magnetic flux only as a physical concept and the magnetic flux density. We will give the magnetic flux a symbol phi m, as you will see during our discussion here, and we will give the magnetic flux density a symbol B. What is the difference between magnetic flux density B and phi m? B is the number of magnetic flux lines that pass perpendicular to a unit area surrounding a point you study. This is B. And what about phi m? Phi m here, it's the magnetic flux. Phi m, it's AB sine theta. A is the area which we are studying here. B is the magnetic flux lines which pass perpendicular to 1 meter squared of this area. And theta is the angle between A and B. Theta is the angle between A and B. So here phi m, the magnetic flux, equal AB sine theta. Theta is the angle between the magnetic flux lines and the area. What will happen if this area is perpendicular on the magnetic flux lines? And what happens if this area is parallel to the magnetic flux lines? If the flux lines parallel to the area, of course any two parallel lines or two parallel planes, here theta will be 0. So phi m will be AB sine 0. Of course sine 0 equals 0, so phi m here will be 0. If the area became perpendicular on the magnetic flux lines, so here phi m changed to be AB sine 90. And of course from your studying of math, you know that sine 90 equal 1. So here phi m equal AB. What about, this is the magnitude of phi m and the magnitude of B. What about the measuring unit of both of these, phi m and B? Of course A, its area, and its measuring unit is meter squared. Phi m, its measuring unit, it's called the magnetic flux, and its measuring unit will be Weber. It's the name of one of the famous scientists in here in this domain of physics. So the measuring unit of magnetic flux density B here will be phi m divided by A area. Phi m, its measuring unit is Weber, and A, its measuring unit is meter squared. So the measuring unit of the magnetic flux density B, it's Weber per meter squared, which equal it's equivalent to another physical measuring unit. It's a Tesla, and the Tesla, by the same way Weber, both names of a famous scientist. But here note these 2 points. If the problem said to you that the coil was perpendicular on the magnetic flux lines, this means that the angle between the coil and the magnetic flux lines equal 90 degree. Hence, the phi m equal AB sine 90. What will happen if this coil or this area rotate angle theta from the normal position? Rotate angle theta from the perpendicular position. So here phi m will change from 90 to this certain angle theta. From here we can calculate phi m by this equation. Phi m equal AB sine 90 minus theta. Why we put here 90 minus theta? 90 minus theta due to the coil was perpendicular, then it changed to be theta. So to calculate the difference between both, it will be AB sine 90 minus theta. But if the problem said to you that the coil rotates angle theta from the parallel location, this means phi m here equal AB sine theta itself, due to it was parallel. This means the angle was 0. So if we calculated the difference between 0 and a certain angle, it will become the same value of the angle. So phi m here will be an sine theta, AB sine theta. Now let us move to study one of the most important parts of physics here, which is the magnetic field due to passing the current in a straight wire. As you see in the figure in front of you, the current passes through a wire. This wire is located in a vertical plane. Here, this is the shape of the magnetic flux lines produced from the passing of this current here. This is called B, the magnetic flux density. The shape here in front of you, number of circles, has the same center, which is the wire itself. So this figure in front of you is called concentric circles. And these lines have a certain directions, can be determined by a certain rules called Ampere's right hand rule. We will study these rules during our syllabus, but here, as you see, these circles get crowded as we get closer to the wire and get away from each other as we go away from the wire. So the shape of magnetic flux lines, concentric circles around the wire, and they are closer together near the wire and far away from each other as the distance from the center of the wire increases. This means that the magnetic flux density B is inversely proportional to the distance away from the wire. B inversely proportional with D, with the distance. As we go away from the wire, of course, the effect of B will decrease. And the magnetic flux density is directly proportional to the electric current intensity passing through this wire, B proportional with I. It's directly proportional. So I can here ask you a question and I'll let you think in this question to discuss it next time together. Uh, this question is why it's preferable to build houses away from high voltage towers around us. Of course, you know these high voltage towers. These high voltage towers carry a high, very dangerous electric current intensity I. Why it's important for us to build these towers away from the houses? Of course, now you can answer this question. I'll let you think in the answer, and we will discuss it together another time. For now, I leave you to practice this part which we studied together, and we will continue our journey together another time. For this time, I want to thank you for your effort with us in physics. Have a good time. Bye.